Hello, honors physics students. On the Google Classroom poster, we're asked to do the ray diagram for problem 7 in the textbook. So hopefully you've already done that. Let's go through what we can see. Okay, so here's part A. First of all, we're looking at a mirror, not a lens, right? So it's been a while since we've done mirror ray diagrams, so hopefully remember that light does not go through mirrors, right? So immediately, if you had light going through the other side of the mirror, please pause the video, start over. You've got to remind yourself what happens here with mirrors. Mirrors reflect light. Alright, so is this a convex or concave mirror? This is concave. We always want to remind ourselves the shape of the mirror, right? The light's coming in this way, it's caving in around it. Does that make it convex or, converging or diverging? That makes it converging. So if at any point you did any of this wrong, you've got to pause the video, you've got to try it again. So we have our parallel ray of light. It's going to reflect through the focal point. I've done the focal ray here. It goes through the focal point on this side, and it comes back parallel. They meet over here. Of course, you could have done the central ray if you'd like to. Remember, how do we do that? That's where we measure the size of the object. You measure the same distance down below. You put a single dot there. You connect the dots. It would work, but I just like to do this one because you know what? There's a lot going on with the central ray. And honestly, if you don't want to do it, you don't have to do it. As long as you get two rays to meet, that's where the image is formed. This is where the image is formed. Everything's looking good. All right, let's go through the math here. Hopefully you did the math first. I mean, you weren't even supposed to necessarily do the ray diagram, so you had to have done the math first. The radius of curvature is 20 centimeters. The focal length here is 10 centimeters, and the math predicted 13.3 centimeters. And if this is 10, that's 20. Does that look like 13.3? You bet it does. Is it inverted? Of course it is. Is it real? Remember, real is not about which side of the optical device the image appears on. It's all about whether you can get it onto a screen, whether the light rays actually meet there. And certainly these rays do meet. You don't have to trace anything back. You put a screen here. If there's some sort of lit object, yes, an image will appear on the screen. That is a real image. Part B, we move it so it's on the radius of curvature. So here's my parallel ray going to the focal point, my focal ray coming out parallel. They meet over here. And let's look at the math. The math says 20 centimeters in front of the mirror, and if you do this properly, it should end up right there on 20 centimeters. That's kind of interesting. Notice that this is f, this is twice f, and so for this converging device, if you put the object on twice the focal length, you end up with the image at twice the focal length. Is it real? Yep. Is it inverted? Yep. Remember, real and inverted always go together for a single device anyway, but certainly if you put a screen here, you would get the image onto the screen. But that's kind of interesting. So is this magnified, reduced, or life size? Well, I think it's the first time you've actually seen a life-size image because the object distance and the image distance are exactly the same. If you measure this, it should be the exact same size as the object, or at least really, really close. And so we see for a converging device, you put the object on twice the focal length, you get an inverted, real, life-size image. It's always good to look for these patterns. Part C, we move it here onto the focal point. Now here's where things get very interesting. My parallel ray comes out through the focal point. My central ray, if you measure down here, comes out like so. Good luck doing the focal ray, right? Because even if you start here and go down to the focal point, that doesn't make sense. You're not going to hit the mirror. If I go the other way, as we've done sometimes, from the focal point up to the tip of the object, you're not going to hit the mirror, and so it's impossible to do the focal ray. What happens, in fact, if you look at these patterns, you see that these rays are coming out parallel to each other, right? And if you trace them backwards, they're still parallel, and so the proper way to describe this is no image. So it turns out when you put an object on the focal point of a converging device, now so I'm not saying mirror or lens, that's going to come up later on. If you put an object on the focal point of a converging device, the rays come out parallel and you form no image. These rays will never converge on either side of the mirror. That's a very interesting pattern, and it's an interesting application. This is how a spotlight could be made. If you have a converging device, mirror or lens, you put the object right there on the focal point, a sort of like a chunk of light will come out, and then you can direct that chunk of light to somewhere to illuminate something. This is how a spotlight could be made. And again, notice I keep saying converging device, not necessarily converging mirror or lens, because the same thing will happen for a converging lens. Okay, so at this point we're going to be going over your homework ray diagrams, so make sure you have your homework in front of you, both Cutnell and Johnson and the textbook. We'll start in the textbook, looking at problem 29. Alright, back to doing lenses. Is this convex or concave? Convex. How do you know? Thicker in the middle, thinner on the edge. Converging or diverging? Converging. Right, these are the questions you really got to be asking yourself every single time. Alright, so my parallel ray goes to the focal point on the other side because it's the lens. My central ray goes straight through. My focal ray comes out parallel. Here's my image. Remember, the ray diagram is not complete unless your image is drawn. You have to draw the image. Notice I'm putting arrows on all my rays. You put arrows on all your rays. This is how ray diagrams are done. Let's look at the math. All right. Oh, sorry, the description, right? So clearly it's inverted, and it's life size and real, right? If I put a screen here, the image will certainly show up on the screen. These rays of light really go onto it, but notice it's life size. How interesting, right? The focal length is 20. It's placed at 40, which is twice the focal length, and we end up at the image twice the focal length on the other side. The size of the object and image are the same. It's life size. We just saw that for the mirror, right? Now we're seeing it for the lens as well. For a converging device, you place the object at twice the focal length. We get an image that is life size. Very, very interesting. Converging lens, DO equals twice F. That's what I was just saying. All right, let's go to letter B. Now we put the object on the focal point. Huh, look what happens. The rays are coming out parallel to each other. We just saw that for the mirror. Now we're seeing it for this converging lens. We get no image once again, right? It's that exact same idea. You put the object on the focal point of any converging device, you'll get no image. Converging lens, DO equals F, just like for the mirror we had done. Here we go to letter C. Now we place the object even closer. It's within the focal length, and we get our parallel ray coming out to the focal point, our central ray going through. These rays are not meeting. What do? We trace them backwards. Here's the focal ray. Remember, it's a little bit tougher. You don't have to do this one, but it's a nice little challenge. Here's where you start at the focal point, go up to the tip of the object. It's going to come out parallel. You trace it backwards. It meets over here as well. Here's our image. Once again, I want to remind you that even though you know you can be tracing this backwards, if you're not drawing this ray coming out through the lens, you're wrong. You are wrong. That's not how we do it, right? We draw the actual rays, then if you have to trace it backwards, you do it. And notice I had to draw that extended line up and down, up above and below the lens, because the lens itself it wasn't tall enough. That's fine. That's how you do it. Make sure you draw the image. Make sure you're putting arrows in all your rays, all the usual stuff. It certainly is upright. It's clearly magnified, and is a virtual image, right? We had to trace the light rays backwards. If I put a screen back here, certainly light goes onto it, but the light has not gone through the lens. None of these light rays are going to go through the lens, then back onto a screen over there, so it's a virtual image. Also, upright and virtual always go together. When you look at the math, we look at the situation here, of course, DO is less than F. For a converging lens, we got this virtual image. Let's go ahead to Cutnell and Johnson. Here we're looking at problem 55. All right, look at this lens. Is it convex or concave? It's concave, right? It's thinner in the middle than it is on the edge. So that make it converging or diverging. That's diverging. So if you have a parallel ray going through the focal point on the other side, that's wrong, right? At this moment, pause the video and you've got to redo it. A lot of students get very good at their converging device ray diagrams, and they totally forget how to do the diverging ones. But you know what? You've got to be good at everything. We literally only have 4 types of devices. 2 types of mirrors, 2 types of lenses. It's your job to be excellent, not good, excellent at every single one. That's your job, okay? So here's our diverging lens. Parallel ray diverges, not just at any random angle up and to the left, but as if it were to trace backwards to the focal point on this side. Remember, we're using sort of like the wrong focal point, the negative focal point, the virtual focal point, because it's a diverging device. Our central ray, it goes straight through. We love the central ray, and you don't even have to do the focal ray if you don't want to, but I put it on here. This is where you start from the tip of the object. You aim for the focal point on the other side. It comes out parallel, and when you trace it backwards, it meets here. Right? Remember, don't forget, we have to draw the image. You have to put arrows in all your rays. It's all the usual stuff. When you look at, oh, it's the concave shape. It's a diverging lens. Let's look at the math here, which of course you did first, right? You did the math first, right? That's my advice. You always do the math first. It predicted 15 centimeters to the right. If here's 25 and there's 0, does that look like 15? You bet it does. Certainly is virtual from all the sign conventions. You put a screen here. There's no way to get the light onto the screen that has gone through the lens. Certainly light's going to go onto that screen, but it hasn't gone through the lens yet. Plus, remember, you're actually sort of blocking light from ever going through the lens. There's no way to get an image onto that screen. Well, we should have predicted that anyway because it's a diverging lens. Right? Diverging lenses only produce virtual images anyway. Let's look at 105. Okay, what sort of lens is this? This is a converging lens. All right, so the parallel ray converges to the focal point. I've drawn the central ray. I've drawn the focal ray coming out here. I had to use the dashed lines above and below the lens. That's fine. We've got our image all the way on the other side. Predicted 18 centimeters to the left. That's what the math showed us. This is 6, 12, 18. It should have been right there on 3F. Okay. Look at 118. Back to a diverging device, concave in shape. It looks very similar to problem 55. Okay, nothing really fancy here. All the same sort of things. These rays diverge. We draw the image over here. And the math predicted 10 centimeters to the right. This is 20. Does that look like 10? You bet it does. Yeah, you definitely should have gotten it right there, halfway between the lens and the focal length. The magnification should be 0.5. You can literally measure the size of the object, measure the size of the image. You should get a ratio of 0.5. As always, if you've done any of these things wrong with the ray diagrams, you've got to pause the video. You've got to try it again. You've got to make corrections. You've got to try and try and try until you get excellent at it.